Look at a modern industrial mining site. To get to the raw gold-bearing rock, crews have to carve out massive, terraced pits, moving millions of tons of earth. This graphic shows the core mathematical problem with low-grade ore. On the left is an entire ton of raw rock. On the right is the yield, a tiny 1.5 grams of gold. At that concentration, the gold is practically invisible to the naked eye. You cannot sift it out by simply smashing the rock with hammers or using mechanical extraction. Instead, engineers use chemistry. They construct a giant chemical coffee filter, a process called heap leaching, which can extract up to 80% of that hidden gold. By abandoning physical crushing and relying on chemical dissolving, mining operations turn mountains of otherwise worthless rock into profitable assets. Before a single shovel hits the dirt, geologists survey the site to confirm the rock profile is suitable for chemical leaching. Core samples are then sent to a laboratory. Here, technicians test different solvents to formulate the exact chemical recipe required to break down that specific site's mineral makeup. This is a strict operational failure point. If the lab tests show they cannot recover at least 50% of the gold, the entire project gets scrapped. Heap leaching relies entirely on this precision chemistry. Confirming the exact solvent recipe in the lab mitigates the massive financial risk of deploying heavy machinery. Step 1 in physical construction is building the leach pad. Engineers lay down a massive, totally leak-proof liner to contain the chemicals and prevent environmental contamination. Next, the raw ore is stacked on this pad. These piles reach up to 60 meters high, roughly the size of a 20-story building. Preparing the ore requires specific geometry. Engineers crush the rock and tumble it with cement and water, binding the loose material into small, porous pellets. If they skip this cement step, the fine dust clogs the pile. The chemical solution will pool uselessly on the surface instead of trickling down. Structuring the physical geometry of the rock pile to ensure it is highly permeable is just as critical as the chemical solvent itself. Operators drip a cyanide solution across the 60-meter ore pile. Over weeks, it trickles down through the porous pellets, chemically stripping invisible gold atoms from the rock. The gold-rich liquid safely pools at the bottom, creating the pregnant leach solution. By combining gravity, extended time, and targeted chemistry, the operation successfully extracts a microscopic solid and concentrates it into an accessible liquid. From the bottom of the pad, the pregnant leach solution is channeled away and pumped directly into a specialized extraction facility. To separate the gold from the liquid, operators typically use one of two mechanisms. They introduce carbon to absorb the gold, or they add zinc to force the gold to precipitate and turn solid. This flowchart visualizes what happens next in the closed-loop system. The leftover barren liquid is immediately recharged with cyanide and pumped right back to the top of the pile to start a new cycle. Once the ore pile is completely depleted of its gold, the site undergoes a massive neutralizing rinse to ensure the remaining rock meets strict environmental safety regulations. The entire process functions as a continuous, zero-waste loop. It maximizes the financial return of the extraction while prioritizing ecological containment. We started with a mountain of dusty, low-grade rock. After a slow, calculated chemical drip, the final output is physical, solid gold bars. A successful operation will achieve a 50 to 80% total gold recovery rate, all without wasting a single drop of the chemical solvent. Heap leaching proves that massive machinery isn't the only solution. Through targeted chemistry, engineers extract value that would otherwise remain trapped in the stone. It makes you wonder, what other low-grade resources are hiding in plain sight, waiting for a similar chemical strategy to make them profitable?